about we start the recording, please?
Done, and I'm going to make you host.
And I say, got it. Okay, so my name is Adrian German, and I was the chair of the Workforce Development TAC in the QED-C last year. And now I'm the moderator of this particular session of e-poster research presentations. This, as you can see on the screen, is session 14. We started about 2 years ago, and we have roughly a session every 2 months. We have 4 outstanding presenters today. You can see them on your screen. I think Christopher Bishop, who runs the office hours with mentorship and industry members and students, has just joined. So the first presenter is Harper Grimsley. I'm going to, for every presenter, it's about 15 minutes, but we never end on time. So in the interest of making sure we capture everything, we're going to continue recording. It might last 90 minutes. We'll post the recordings. I think we shouldn't sacrifice anything if there are questions and people want to know things. So Harper Grimsley has received a bachelor's degree, 2, in chemistry and mathematics at the University of Arkansas in 2018. And he's currently a 5th-year chemistry graduate student at Virginia Tech. He plans to graduate this fall. You have the title of his presentation, and for every presenter, I asked them to describe the research in terms that would resonate with the high school students in such a way that it would spark their interest and imagination. He says, studying quantum systems such as molecules is a hard problem because classical computer bits are bad at simulating these systems. Using quantum systems to simulate quantum systems is an attractive alternative. One of the best algorithms that we have for this, called the variational quantum eigensolver, or VQE, involves measuring chemical energies on quantum hardware based on a set of variables which are optimized on a classical computer. One problem that is frequently observed with this approach is the prevalence of high energy local minima. Getting trapped in a local minimum hinders the accuracy of the VQE in predicting molecular energies, making it less useful. In this talk, he will demonstrate that his adaptive problem-tailored adapt VQE consistently finds good minima, even when many poor local minima are present due to its unique quantum circuit design. So Harper, welcome, take it away.
Okay, thank you for that introduction. I'm gonna share screen here. Okay, so yeah, I'm gonna dive right in to details of classical optimization and adapt VQE. So letting your quantum computer store your wave function is an attractive prospect because you can theoretically map one spin orbital to 1 qubit instead of a much worse factorial scaling that is emblematic of classical computing. One of the most popular algorithms for this is the VQE, variational quantum eigensolver. The idea of a VQE is to outsource optimization to a classical computer, but to do measurements and state preparations on a quantum computer. So the goal of a VQE is to minimize this energy E, where H is the system Hamiltonian, theta is some classical set of parameters, and psi is our ansatz. And that if that sounds like a very broad class of algorithm, it's because it is. There's a lot of freedom in how you choose what psi of theta could be. And our group's prescription is the adapt VQE algorithm. So in adapt VQE, you start with some preordained pool of generators, A1 through AN, and these are anti-Hermitian operators. They can be whichever anti-Hermitian operators you want them to be. You will start by initializing some simple ansatz, such as the Hartree-Fock such as the Hartree-Fock state. You will measure the gradient of each operator if you were to add it to the pool with parameter 0. Assuming you're not converged yet, you will select the operator with the largest gradient and actually add it to the ansatz with parameter 0. So you're adding e to the theta equals 0, an plus 1. So that's your new operator. And then you'll re-optimize all the parameters in the ansatz. So this is itself a VQE subroutine. You repeat these steps over and over, adding one operator at a time until you've achieved some convergence criteria. Generally, the norm of this gradient vector is going to be small, and that's how you know you're done. So here's a comparison of adapt and some other methods. Adapt is given in purple. The x-axis is the number of parameters. So as you proceed from left to right, adapt is adding one operator at a time. The y-axis is your error from full CI, i.e. exact diagonalization. So adapt is in purple. Compare that with, for example, the UCCSD onsats, which is a classical chemistry approach that adapt is sort of based on, at least one of the original pools. And you see that adapt is doing way better at the same number of parameters. And adapt is achieving a level of accuracy in fewer parameters that UCCSD is just not achieving. You can also compare different random orderings. I'm not going to go into what these are, but different random orderings with different pools that are building a circuit up in the same way as adapt, but without this gradient criterion. And you see that adapt does far, far better. So it is, in some sense, a quasi-optimal ordering of the onsats. So a complication of this, and the subject of more recent work, is the classical part of this optimization. So far, we've just focused on building a good psi, but we also have to train the parameters theta at each step. And this can be hard due to problems like local minima and barren plateaus. So local minima should be familiar from high school calculus. They have an unfortunate tendency to appear in VQE landscapes. The idea is just that you have some higher energy that you're getting stuck in on the cost function landscape. So as a case study, consider linear H6 at 1 angstrom. Here is another adapt plot where you've got the x-axis is the number of adapt steps, y-axis is error from full CI. This red curve is what happens after you've done adapt using the HF guess, which is just setting all of your parameters equal to 0 at the beginning of each optimization. This happens to be the same as the recycled guess, where you reuse all your old parameters from the previous adapt step. But when you add in random guesses, things start getting interesting. So at each point here, there are 300 initializations used, and then they're optimized as far as BFGS can take them. So what you see is that even after optimization, there's this massive spread of several orders of magnitude in accuracy of the local minima. And there's a very large gulf between the chemically informed HF and recycled guesses and these random guesses. So what this tells us is that it matters a lot how you initialize, and it's very hard to do better than the recycled and HF guesses. So one thing you might ask is what happens when you make this problem harder? What happens when you make it more strongly correlated by stretching out the H6 to 3 angstroms? Well, suddenly HF doesn't look so nice anymore, which isn't surprising because it's now strongly correlated. HF is a worse approximation to the actual wave function. The recycled still looks pretty good. It is occasionally getting beat by the HF, but we think that's less and less likely as you get more and more strongly correlated. And the random guesses have the same spread really as before, with the exception that now you're able to sometimes do better than the best. The best random initializations are sometimes able to find better local minima than the recycled guess. But in general, the recycled guess is quite good and is more than competitive with the idea of using a random initialization. If you had to bet on one initialization, on one given initialization being one of the better ones, the recycled one is it. So why is adapt doing so well here? Because it's clearly generating very difficult surfaces to optimize on, and yet its own parameters are yielding good minima. We think that it's benefiting from a type of burrowing effect where you can be in a local minimum and adapt will just keep digging down, down, down. And that's shown diagrammatically here, where adapt's burrowing into one minimum versus an over-parametrized type landscape where you just avoid having traps altogether. We know that it's expensive to get an over-parametrized circuit. So if we can achieve a deep deep local minimum or just a good minimum without getting this kind of landscape that's really attractive to us. So barren plateaus are kind of the other aspect that is really problematic of the classical part of the VQE optimization. Barren plateaus are landscape features associated with exponentially vanishing gradients. These are equivalent to narrow gorges, which is just a concentrated region of the cost function. You can see that diagrammatically here. The blue curve is a nice one. The green curve has a barren plateau, and in the middle of it is a narrow gorge. Right. So by construction, adapt is only going to start an iteration if it can resolve a non-zero gradient because of its design in using the gradient as the criterion for operator addition. Consequently, we expect that barren plateaus are a non-issue for adapt during optimization. However, it could still get stuck during ONSAT's construction. So we look at this a little bit by considering H6 at 1 angstrom again. We look at 71 parameters, so the last step here, and we're looking at the recycled solution. So this is what adapt would do, the standard adapt. And what we're doing is looking at the cost function landscape, which is a 71 parameter energy function. And we're looking at the parameter range from adapt in a 71 parameter hypercube with radius given by the x-axis here. And the y-axis is the variance in the gradient norm. And what we see is that it spikes right next to the adapt solution and then settles down at a much lower value as you get further and further away from the adapt solution. And what this tells us is that adapt seems to live inside of the narrow gorge. We seem to have a landscape that looks like this green curve, and adapt is in the part of it we want to be in. So just takeaways. VQEs are a powerful tool for quantum computing. They introduce both quantum and classical problems. Adapt VQE helps address both with its adaptive ONSAT's construction and robust optimization. And we think this makes adapt a promising tool for future research into VQEs in general. I want to thank the Mayhall Economy of Barnes groups, DOE, NSF, ICTAS. Feel free to email me or check out my GitHub. And I am graduating this fall and looking for work if anyone's hiring. Thank you.
Okay, so thank you, Harper. And we wanted this to be a two-way conversation. Now we open it for questions. If anybody has questions from Harper, feel free to either write in the chat or speak up. I want to mention one thing though. We asked every presenter if they have any questions for us or for the industry members in our consortium. So Harper said he'd be interested in knowing the hiring plans as they relate to a quantum algorithm specialist and he mentioned Zapata, QCware, Los Alamos, IBM, Google, Amazon, and Rigetti later this year. So with this, anybody, any questions or answers?
Yeah, I had a question. This is Sean Blakley here. So Harper, when you refer to the parameters here, these parameters theta, give me an example of theta. Like what is a theta in your algorithm?
It's just some number between 0 and 2 pi usually.
What does it represent? That's what I'm trying to.
Oh, I'm sorry. Yeah, that's a good question. So the actual ONSAT's form is given in this highlighted area. So it's essentially parameterizing this rotation by the operator A.
I see. So it's basically like a phase parameter or something that you would that you tack on to the new exponential for the next iteration of the operator pool.
Something like that. Yes.
Thanks.
Yep.
Okay, so in the chat, we have a link from Terrell, who is the vice chair of the Workforce Development TAC. And he said, Harper, see, there's a link, Quantum Consortium, Quantum Jobs. So that's one starting point. Anybody, any other questions for Harper? With your permission, I'm going to ask Christopher Bishop, when is the next office hours? I'm so sorry.
Yeah, no, I was just going to, hello, everybody. I was just going to put it in the chat, actually. The next office hours is Thursday, June 30th from 9 a.m. to 1 p.m. Eastern time. And if you want to sign up, they're casual, informal conversations between students and mentors from the QED-C, students studying quantum information science related subjects. So Harper and all the students on the webinar, on the session today, I encourage you to sign up. You can send an email to our task ID, which is, I'll put it in the chat, but it's officehours@quantumconsortium.org. So hope to see you there.
So it's not completely booked for the next one. Still some
No.
openings.
Yeah, still have openings. So please join us.
Okay, because the previous one was full very quickly.
Yes, it was. Thanks,
Okay, so-
Adrian.
Well, you're very welcome. So it's now 3:15. Should we move on to the second presenter, or does anybody have any other questions?
Could I ask a question?
Yes, please.
So with this algorithm, how does it compare with shots as well? So like, is it expensive as well? Like because taking the derivatives, like you need to take more like shots, right? So just a question, like if you've compared that.
I don't know the shot numbers off the top of my head, but yeah, you do add a lot of shots from taking these derivatives, and you add a lot of shots from the fact that you're doing essentially an entire VQE every iteration up until the last one. The hope is more that you save on circuit depth than that you save on shot.
Yeah, no, that makes sense. I was just wondering. Thanks very much.
Oh, no problem.
And thanks to Jeff Joy from Cold Quanta, who posted a brief note for Harper and everybody else in the chat.
Oh, thank you.
So let's move on to the second presenter, whose name is Andi. He just graduated from UC Berkeley with a major in physics and computer science. He was first introduced to the world of quantum computing in his junior year when he joined Professor Siddiqui's quantum nanoelectronics lab, and he has been fascinated with the subject ever since. He's become recently interested in quantum complexity theory and the ways in which quantum information interacts with classical statistical learning theory. Next year, he will be a first-year PhD student at Harvard in the quantum science and engineering program. So with this, Andi, take it away.
Perfect, thank you. Okay, great. Thank you, Adrian, for the kind introduction. I appreciate it. So before I get started, I just want to acknowledge none of the research I'm presenting today would be possible without the wonderful people in the quantum computing group at Los Alamos, led by Patrick Coles. Okay, so the topic of my talk today is going to be aimed at addressing one question, which is how can we feasibly realize variational quantum algorithms on near-term quantum hardware by improving the classical part of the VQA algorithm. Okay, so first to give a very brief primer on variational quantum algorithms, since Harper did such a good job, I'm going to try to make this very brief. So more specifically, I'm going to be talking about the variational quantum eigensolver, which is aimed at estimating the ground state energy of some arbitrary Hamiltonian that you're free to specify. Typically, it might be something like a molecular Hamiltonian. So it's based off the variational principle, which simply says that any state that you prepare, if you evaluate the expectation value of the Hamiltonian on it, it's going to be greater than or equal to the ground state energy of the physical system that you're looking at. So the basic idea is then we encode psi in some quantum circuit or some ansatz. You're free to choose this ansatz. You know, maybe you can determine it by using adapt VQE or something like that. And then once you've set your ansatz, the nice part of using quantum hardware is that we can quickly evaluate some cost function f of theta, which is actually defined to be the expectation value of the Hamiltonian on your parameterized state. And then the whole idea of VQE is to classically minimize this cost function. And then for an ansatz that's expressive enough, we believe that the minimal value of the cost function will be a good estimate of the ground state energy. Okay, so now the question basically reduces to how can we minimize our cost function as by varying the parameters theta. So this would be basically one part or the subroutine in the adapt VQE algorithm that was discussed previously. So we used a very popular idea from classical machine learning. It's very powerful, which is essentially we use the gradient. And unlike classical optimization, we don't have access to backpropagation to calculate the gradient. So what we do instead is that we use the fact that for rather general class of ansatzes, the gradient is also expressible exactly in a form that's known as a parameter shift rule, which is essentially expressing the gradient as the difference between cost function evaluated at two different points. The main problem with this is that we only have access to noisy estimates of f, and since the gradient is defined in terms of f, we also only have access to noisy estimates of the gradient. So this puts us into a regime known as stochastic gradient descent. So what can we actually say about the performance of the stochastic gradient descent algorithm? We want to get some rigorous performance guarantees on what we can say about how well our VQE is going to do. Under certain assumptions, probably the most important of which is that our cost function is strongly convex. So I can discuss how reasonable that assumption is later. But under that assumption, and with the correct setting of the learning rate, the expected improvement in the cost function every single iteration scales with this formula that I've put up here. So it scales linearly in alpha, which is the learning rate. And then you have this positive term, which is the squared norm of the gradient. And then you have a negative term, which is the noise in each component of the gradient divided by the number of shots you use to measure that component of the gradient. So the heuristic takeaway that I want you to have here is that you basically have one positive term, which is signal, and then you have one negative term noise, which detracts from the performance of the algorithm. So if you're not careful, the noise term can overwhelm the signal term, in which case the two will balance out and you won't be able to make any further progress. However, we want to be careful about how we adjust the noise term by basically tweaking each of the individual SI, or the number of shots we use, because we don't want to be wasteful. When we have a large signal, we don't want to use too many shots, and when our signal gets small, that's when we really want to get more accurate estimates of the gradient. So what we do is, roughly speaking, look at the scaling behavior of this equation. So the signal term scales with the gradient squared, whereas the variance scales only linearly in the absolute value of the gradient. So what does this tell you? Well, near the beginning of the optimization, you expect the signal to dominate because you expect the gradient to be very large, right? Presumably, you're initializing your VQE somewhere that's pretty far away from the true optimal value, so you have a large gradient. However, near the end of the optimization, when you're reaching kind of the basin of the loss function, you expect the gradient term to be much smaller, and then therefore you see that the noise begins to dominate over the signal term. So that's when you really have to put in more shots to make sure that you can still make improvement. Okay, so to kind of formalize this, what we really want to do is we want to optimize our optimizer using an idea that we term the coupled adaptive number of shots. So in 2020, my collaborators introduced something known as ICANS, or individual coupled adaptive number of shots, which was that they basically looked at the expected gain every single iteration, and then they optimized that with respect to each individual measurement configuration SI. So they basically, you're trying to maximize the bang for your buck as a function of the number of shots. So we found this rule that kind of conforms to our intuitive understanding that when the noise begins to dominate over the gradient, that's when we need to start increasing the number of shots. So the noise is in the numerator and the gradient is in the denominator. And with this, we actually have very good empirical performance, which I'll be showing on the next slides. But more recently, we actually proposed an extension to the ICANS algorithm known as GCANS, where we optimize the measurement configuration over all the measurement configurations simultaneously. So with that, we actually got a different prescription for the number of shots used in each component of the gradient that heuristically looks kind of similar, but is slightly different in that it's coupled to, or each measurement configuration is coupled to what's going on in other components of the gradient as well. So what was the reason for this? Were we just being pedantic? Well, not really. One important benefit that we're able to get using this optimizer is that we can make theoretical guarantees about how well our algorithm is going to do. So the optimality gap as a function of the number of iterations vanishes geometrically. So in other words, to get epsilon error, we need only log 1 over epsilon iteration. So we get very fast convergence, basically. Okay, so now I'm going to show some numerical results to kind of back up what I've been saying about the CANs idea, the coupled adaptive number of shots idea. So we're comparing here GCANs versus other generic optimizers on molecular Hamiltonians, so dihelium and ammonia, dihelium on top and ammonia on bottom. So the optimizers we compare against are just generic stochastic gradient descent, as well as the atom optimizer. And you can see highlighted in orange, GCANs outperforms both all three of the other optimizers, both with respect to the number of shots and the number of iterations it takes to reach chemical accuracy. Another thing that we wanted to do was compare GCANs versus ICANs. So we basically tried to run VQE on a transverse field Ising model problem. And then we found that even as we scaled up the system size, the performance gap between GCANs and ICANs remains. So GCANs, the performance improvements from GCANs does indeed hold as you scale up the system size. And one last thing, one big benefit of using this CANs idea, or the adaptive number of shots, is that the optimizer performance is not sensitive to hyperparameter settings, such as the learning rate. So we varied the learning rate around a certain range, around like a known optimal value. And we find that stochastic gradient descent and atom, their performance is significantly degraded compared to the CANs optimizers, which are not so degraded. Okay, so the outlook is that GCANs is bringing us closer, one step closer to feasible and successful application of VQE on NISC hardware. We're not all the way there yet. As you can see, GCAN still takes $20,000 to run an Amazon bracket, even for a very simple problem such as ammonia. So, we have a ways to go. However, one main takeaway that we understood from this was that creating quantum tailored adaptations of classical algorithms is a very fruitful approach for designing feasible quantum algorithms to run on near-term hardware. So with that, thank you for listening to my talk, and I'd be happy to take any questions that you might have.
Thank you so much for your presentation, Andy. So as again, in the interest of making this a two-directional conversation, the one thing that Andy said he would be interested in was, he said, I would be curious about Sandbox AQ's current interest in quantum algorithms research, and specifically their vision for their PhD residency in simulation and optimization. And a question for Andy, what will be your next steps in trying to make this, in trying to improve the feasibility of VQE on near-term hardware?
Yeah, sure. So one particular assumption that I kind of addressed earlier on in my talk was we assumed that the loss function was strongly convex in order to get some of these results. And, it's not clear in general under what scenarios your loss function will indeed be strongly convex. And actually, so Harper's work kind of indicates if you use adapt that you can sit within the region, you can be fairly confident that you're sitting within the region of the cost function that is strongly convex, or kind of in this basin around the local minima, or around the global minimum. So that's something we want to look at, kind of integrating together with GCANs to see if we can get better performance.
Okay. Anybody else? I think in the chat we have something.
Yeah, I had a question. So what was the hardware that you used, and what's your strategy in picking quantum hardware from Bracket?
Got it. Okay, so to be clear, we did not actually run this on Amazon Bracket. We ran this on simulated quantum hardware, and then basically calculated the cost, right? So we required the X number of shots, and then we looked at the Amazon Bracket pricing for like, what's the price per shot, and then just calculated what Amazon Bracket would have actually charged.
Okay.
Yeah, we definitely did not have the funding to just spend $20,000 on Amazon Bracket.
Thank you.
Yeah. Sorry if that wasn't clear.
Okay, any other questions? If not, in the interest of time, we're going to move on to the third presenter, who is Sean Blakley. And we have a special setup here. I'm going to play a video. Sean is here. Because I'm playing the video, I'm going to stop no, I can't stop my video, can I? I see. I can share the screen, stop the video. I need to make sure that I share the sound. I do already. And let me briefly introduce Sean. Sean is here. Sean, congratulations. He had a baby. The baby is sleeping behind him. And so we are doing the video so that the presentation wouldn't be stopped. But at the end, he's going to take questions. So Sean Blakley is an NRC postdoctoral fellow in the Nanoscale Device Characterization Division, NDCD, of the Physical Measurement Laboratory at the NIST. Working under Robert McMichael, Sean's research includes quantum sensing of magnetic fields with nitrogen vacancy centers in diamond and improving measurement efficiency and speed with hardware-accelerated Bayesian machine learning algorithms. Sean did his undergraduate work at the University of Texas at Austin, working on beam maintenance and alignment on the Texas Petawatt laser. Sean's doctoral and postdoctoral work at Texas A&M University under Professor Alexei Zheltikov involved developing a new class of fiber-coupled diamond quantum sensors with applications in biology and magnetics. So normally I say, Sean, take it away, but I'm going to start the video and hopefully everybody can hear it.
Today, I'd like to tell you about my work on hardware-accelerated Bayesian machine learning for applications in quantum sensing. Okay, so what is Bayesian machine learning? Well, there's a specific kind of machine learning that we do using Bayesian statistics. It's called optimal Bayesian experiment design. So what is optimal Bayesian experiment design? We call it OBED. OBED is an experimental technique that we use to reduce the number of data points needed to make a measurement. This differs from the more familiar scan and fit measurement technique that involves taking a lot of data in sequential fashion and then fitting at the end of the scan to extract the parameter of interest. The scan and fit technique requires just let me turn my pointer on here, requires a lot of data for averaging if your signal to noise of your measurement is low. And this is especially problematic if you need a large scan range because the thing you're looking for moves around a lot, or you aren't too sure where it is in the first place. For example, trying to find an optically detected magnetic resonance frequency for a single nitrogen vacancy center using the standard scan and fit technique can require over 1 million data points collected over 140 scans just to get an accurate fit for the resonance frequency, shown as this little dip here, fit for the resonance frequency of interest. In these cases, much of the time spent in your ODMR spectrum is wasted collecting data points that don't meaningfully contribute to your fit. But what if there was a way you could only measure the good stuff? What if you could just measure the area around a region of interest without actually having to waste time measuring all these other data points that don't contribute anything useful? OBED is an experimental technique that does precisely that. By using previously collected data points to decide the experimental settings used to collect the next data point. And this often results in orders of magnitude less data points required to make an accurate measurement, but comes at the cost of increased computational time spent between measurements. So how does OBED only measure the good stuff? OBED is a computational technique that uses experimental data to suggest which experimental settings are likeliest to result in a good measurement. To do this, it must first determine how well the measured data agrees with the your physical model for the system. This physical model could be any function that describes the behavior of the system as a function of model parameters. For example, amplitude and phase for sinusoidally varying data, or peak amplitude, full half max, resonance frequency, and offset for optically detected magnetic resonance measurements. This is done in a two-step Bayesian inference subroutine, where the probability that the model function describes the measured data point is calculated using a Gaussian function of the experimental noise, that's sigma, and the collected data value, data point value, which is y sub n, and the model function here, which is f of the model parameters theta and the experimental settings used to make the point d sub n. This probability calculation is performed for the full set of model functions built from all possible combinations of the model parameters theta and model parameters theta. forming what's called a likelihood set, which is then updated using Bayes' rule with the prior likelihood set from the previous measurements, forming the posterior probability distribution known as the posterior. The experiment design subroutine uses the posterior probability distribution to find which experimental settings result in the largest increase in relative entropy from the previous measurement. The experimental setting with the largest relative entropy is likeliest to result in a good measurement. How is OBED implemented in a real experiment? So we introduced the OBED software calculation between data collection and the setting selection steps for our nitrogen vacancy magnetometer apparatus. This system uses a nitrogen vacancy diamond, an NV diamond excited by a laser whose photoluminescence amplitude decreases when an applied microwave field is at its magnetic resonance frequency. This optically detected magnetic resonance frequency changes as a function of the magnetic field environment around the diamond, allowing magnetic field information to be read out optically via the NV diamond photoluminescence. The ODMR acquisition time is set so that the signal to noise of the measurement, signal to noise ratio of the measurement is near 1, and the performance of the OBED technique is compared to the scan and fit technique. The scan and fit technique collects 8,000 photoluminescence amplitude data points as a function of frequency of the applied microwave field, generating an ODMR spectrum. This ODMR spectrum is then used. This ODMR spectrum is averaged many times, and the ODMR resonance frequency extracted from the fit to the ODMR spectrum is plotted as a function of the number of data points, where each dot here represents 8,000 data points, which is one scan for the collect and fit method. The OBED technique starts with a random frequency setting for the first measurements, and every subsequent measurement is performed with a microwave frequency setting determined by OBED. The ODMR resonance frequency determined by OBED is also plotted as a function of the number of data points. The OBED method is found to require 40-fold less data to achieve the accuracy in the ODMR resonance frequency to achieve the same accuracy in the ODMR resonance frequency as the scan and fit method, and can operate at a measurement bandwidth of 100 Hertz, depending on the computational hardware. So far, the experimental performance of our software OBED tool has been pretty impressive, but it's only really applicable in situations where the rate at which you take data is much slower than the time it takes to perform an OBED computation. In our case, that limits us to about 100 measurements per second. Some experiments can collect data at a much faster rate. For OBED to be useful in those situations, you need to have either a faster computer or a faster OBED calculation. Since computational resources are ultimately finite, we investigated what computational bottlenecks were holding the OBED software back. It turns out that most of the time in an OBED calculation is spent determining the utility function. It's this guy right here, which is in the experiment design step. To address this bottleneck, we need to find a utility function that is easier to calculate. In general, a utility function is just an expression for the relative entropy between the previous measurement and the next, the relative increase in entropy. This is determined by evaluating this sum involving a double integral over all possible measurement values and all possible experimental parameters. This is obviously computationally unfeasible for high-speed measurements, but it turns out that you can make a few simplifying assumptions to reduce this to a much easier function to evaluate. If, for example, you assume that the experimental noise is Gaussian, you can reduce this double integral to a statistical range of a small sample of model function values. Since this statistical range is just a difference between the maximum and minimum values of the set, this is much simpler to calculate than the double integral. This min-max utility function results in about a 10-fold reduction in time spent in the experiment design subroutine calculating the utility function, and provides an overall 2.5-fold improvement in processing time for the OBED calculations. This improvement in measurement bandwidth of our software, OBED implementation. It improves the measurement bandwidth of our software OBED implementation to 250 hertz. Furthermore, it turns out that there is basically no penalty to your rate of convergence to an accurate measurement result when compared to other utility functions, including the full relative entropy utility function. You can see that in this plot here is which is standard deviation of your parameter of interest as a function of number of data points, and for all the various different kinds of utility functions, and they all perform at almost exactly the same rate. All converge at almost exactly the same rate as the min-max, and the min-max only requires, like 1/10 the time to calculate. So 250 megahertz, 250 hertz bandwidth is sufficient for slow measurements that need long acquisition times to achieve a reasonable signal to noise ratio. But what if you have a good signal to noise ratio at shorter acquisition times? For example, magnetic field sensing with ensembles of NV centers is one example of this, where the emission rate of the ensemble is high enough that photon counting is no longer necessary. And a photodiode is all that you need to do your data collection. A typical photodiode has a bandwidth on the order of about 1 megahertz, which is much too fast for even the fastest computer running our latest min-max OBED software. In order to extend the usability of OBED to measurements of this kind, hardware accelerating the OBED computation is an attractive solution. Hardware accelerated OBED is no simple task, however, as it has unique design requirements due to its inherent computational complexity. Generally, when the number of unique operations is high, a general purpose CPU is the tool of choice for arbitrary mathematical calculations. However, despite being computationally complex, OBED is highly parallelizable, and the number of parallel computations that a CPU can perform is limited. Highly parallel calculations are often amenable to acceleration using a GPU, using GPU's thousands of computational pipelines. While OBED is highly parallelizable, each individual calculation is generally too complex for the GPU to manage, given that they excel at doing many simple things like simple calculations like multiplication and addition in parallel. This leaves the FPGA as our tool of choice for accelerating OBED. In an FPGA, it is possible to create many custom computational pipelines with specialized arithmetic in parallel, which is exactly what OBED requires. So we developed an OBED hardware architecture suitable for use in an FPGA based around custom designed Bayesian compute cores that implement the higher speed algorithms developed previously, like the min-max utility function and a quartic evaluation of the Gaussian likelihood. Hundreds of these Bayesian compute cores can be instantiated in parallel to batch process the entire space of model function parameters and candidate experimental settings in just a few clock cycles, resulting in a projected measurement bandwidth of over 1 megahertz, while possessing a similar convergence rate compared to the software OBED method, which we compared running 500 data points. So after 500 data points, we determined that we had maxed out the accuracy using the software method, and that was done with signal to noise ratios between 3 and 4. So it's quite competitive. All right, so just as a quick recap, software OBED is ideal for improving efficiency in slow measurements, while hardware accelerated OBED can extend this improvement to efficiency to measurements that are over 1,000 times faster than what OBED can handle. Both of these techniques fit with our general design philosophy for OBED, meaning that they are completely general and application agnostic, user customizable, and provided as free open source software on our group's GitHub page. So with that, I'd like to thank you all for coming, and thank you for listening to my talk. If you have any questions, please feel free to ask them now, or you can contact me at my email address here at NIST. You can also check out our software. We provide it free and open source on our group's GitHub page. And lastly, I'd like to acknowledge my postdoc advisor and Robert McMichael and my colleagues Sergey Dushenko and Jaden Kraft. Thank you so much.
I don't know what happened to sound at the end, but this was the end of the presentation. Let's see, I'm going to keep that up. As I said, Sean is here. So before I open it for questions for him, I'm going to mention the question that he is asking of our industrial partners. He says, what role do you foresee for solid state qubits, like color centers in diamond, silicon carbide, boron nitride, and so on, playing in the future of quantum computing and quantum information science? Are their room temperature capabilities sufficiently attractive to warrant further investigation as candidates for quantum computing? And he can elaborate on this or take questions now.
Thank you, Adrian.
So, Sean, can you hear me?
Yeah, I can hear you. Can you hear me?
I need to stop sharing or what? So I don't think I can hear you. I'm not sure exactly what's happening. Maybe. Okay, so can you try again? Tell me if you can hear me, because Sean, I can't hear you. I know you set up the sound in the beginning. Somebody else can hear me, for example, I'm not sure.
I can hear you, Adrian, but I can't hear Sean. I heard him before.
Oh,
Now, Sean, you're on mute, right?
So somebody asked about the number of technologies. I posted that in the chat, 9 different types of technologies across 16 different quantum hardware manufacturers.
Where'd that come from, Kevin?
So this is from Denise at Adam.
Okay, thank you.
Can y'all hear me now?
A little bit.
Okay, hold on, let me change my audio settings. 1 second. Oh boy. Okay, y'all can hear me? No?
It's really quiet.
Oh, it's really quiet. Let me move in real quick. Is this better?
Yeah.
Great. Sorry about that. I don't know what happened there.
yeah, I don't know.
Can't hear you.
Okay, so let's see. And can somebody hear me now? No?
Yeah, we can hear you.
I'm very sorry for that. I had trouble, and then Sean a little bit of trouble, and so I wasn't sure exactly what was going on. Sorry about that, but Sean, are you available?
Sean, it sounds like your mic is turned off. Maybe check what input device you have selected in your sound settings.
He did change the settings in the beginning. He set them up specifically, and it was working fine for a while.
Can y'all hear me now?
Yeah.
Now you can hear me?
Yes.
Oh, thank God. I don't know what happened there. It artificially muted or dropped my microphone volume to like nothing. So sorry about that. Anyway, I'm happy to take questions if we still have time.
Hey, Sean, so this is Chris. Question, is this work being exploited at NIST? Like, what are you doing from where you sit, like to take this very cool approach, into to the next level or apply it in real world settings? Or
We are exploiting this at NIST, and we're also sort of, I can't really call it contracting, but we're assisting other people outside of NIST in using this as well. So the main thing is that so I'm assuming you're talking about the software Bayesian stuff. The Bayesian experiment design technique is completely application agnostic. And so a lot of time we get a question, which is, can I apply this to my experiment, right? Can I use this to make my experiment more efficient? And so the answer to that the answer to that requires two criteria. The first criteria is that does your experiment have, or rather, is your experimental data a result of an input that you can control? So like if I'm adjusting a knob, like a frequency or something, and reading the data output, if that's the case, and the data changes as a function of something I can control, then in principle, OBED, opt-based experiment design, can be applied. The second is, do you know something about your system? So for example, do you know what your data should look like? For example, if you're looking for a resonance frequency, you know your resonance frequency has a Lorentzian line shape or something like that. So you know that approximately your data should have some kind of Lorentzian format. That if you know something about your data and your output is a function of an input that you can control, then the answer is yes, OBED is applicable. And then the question is it good? Is it helpful? And that question is basically, do you already have enough efficiency in your measurement that you don't care? And if the answer is no, then yeah, you should try it and see if it improves it. And then to more directly answer your question, yeah, we are already investigating applying it to other people's experiments elsewhere at NIST and again in a broader industrial setting.
Great, thank you very much, Sean. Appreciate it.
Thank you.
So I was kind of confused. Where does this fall under quantum sensors?
This is that's a good question. This is a computational tool that we are applying to quantum sensing. So this is basically a general tool that we have tailored to use in a quantum sensing environment. This computational tool we have, it's not a new computational tool. Bayesian experiment design has been around now for quite some time, but we have adjusted it and modified it to be more efficient, and then also made it applicable to a wide variety of certain class of quantum sensing experiments. And this, of course, it's completely general though.
And could you help demystify to some of us quantum sensors as far as release date? Because you see like PAR sensors online.
Yeah, that's completely reasonable. So a quantum sensor is a sensor that uses some quantum phenomena as the basis for its measurement. So for example, if I want to measure magnetic field, a quantum sensor would be something that, for example, uses the spin of a quantum state and the Zeeman effect to quantify the magnetic field. So how much the Zeeman effect splits the spin resonance of a quantum system. So that's sort of like a canonical quantum sensor is something that exploits some quantum phenomenon to do a measurement, or to sense something, like for example, magnetic field.
Okay, and then how many are there? How many different types of quantum sensors?
That's a part of my laughter. That's a really good question. There's a lot, and they're really different. So for example, I gave you a spin-based quantum sensor. There are other quantum sensors where you can do like where you can look at like use entanglement. You can use like what do you call it? Like ghost imaging and things like that, where you absorb a photon, one of a pair of entangled photons, and you look at the result of you look at the outcome of the other entangled photon to make it like a surface image or something like that. And then there's also other stuff with quantum states like noon state measurements. It's a very broad class of measurement categories. There's just all kinds of different stuff and different sensors, different sensing modes, etc.
Awesome. Okay, thank you.
So I think Kevin has posted a picture. The picture looks like a slide from Denis Rufner, I think, with the 9 qubit modalities, and then the squares are supposed to be proportional with, I don't know, investments or the size of the companies involved. Is this an answer to Sean's question? Sean, did you see the picture that?
I didn't see it in the chat. I'm assuming it was posted in the chat. I didn't see it there.
Yeah, I didn't see diamond, but I think it's just like a kind of like the state of the industry, just a rough overview.
There's a color center square. Okay, well, I can send you the slides separately.
That would be great. Thank you.
So we're going to move on to the fourth presenter. With apologies, we always do this. We always end up taking a little bit more time, but fortunately this is recorded. And the fourth presenter is Haifeng Qiao. He received his bachelor's degree in physics from Kenyon College in Gambier, Ohio, United States. He is currently pursuing a PhD in physics at the University of Rochester under the supervision of Professor John Nickel. Haifeng's research primarily focuses on spin-based quantum computing in gate-defined semiconductor quantum dots. Specifically, he focuses on developing and experimenting with different methods of transferring quantum information across an array of electron spin qubits. So with this, please go ahead.
Thank you, Adrian. So let me share my screen real quick. All right, how does it look? Can everybody see my screen? Perfect. So, all right. So my talk is going to be a little different from the rest of the talk today. My work is not related to quantum software or algorithms anyway. Instead, what I'm going to show is some of the experimental results that I had in something called the Fouquet enhanced spin swaps. And to be more specific, we demonstrate a way to improve the quality factor of the spin eigenstate swap. In other words, the projection swap in a semiconductor quantum dot spin array using a Fouquet sequence. So first, I'm going to cover a little bit about the background and motivations for my works. So the electron spins in semiconductor quantum dots is a promising platform for quantum computing applications due to the benefit of long coherence times and scalable architecture. The host materials are usually layered semiconductor heterostructures, similar to what's shown here. And it's engineered to create a thin sheet of two-dimensional electron gas at the interface. And the electron gas can be further confined into the isolated islands by the metal gates on the surface of the wafer. And you can apply the voltages to the metal gates to control the chemical potentials of the electron spins. And once you have isolated individual electrons, there are several ways to encode your spin qubits. And currently, the most common way is to use the spin up and down state of a single electron as a two-level system. You can also use 2 electrons to form a single triplet qubit, or 3 electrons as an exchange-only qubit, which all have been experimentally demonstrated. There are also proposals of using 4 electrons to create something called a singlet-only qubit, which I don't think has been experimentally demonstrated yet. And in the past few years, many studies and researchers have developed and drastically improved the control techniques of quantum dot devices, such as the overlapping gate architectures, more precise chemical potential controls, and rapid high fidelity readout. And one important area of research, as shown on the right here, is the transfer of quantum information, which aims to achieve high connectivity between qubits. And this is essential for error correction, high fidelity readout, and many other quantum algorithms. And there have been many proposals and experimental demonstrations of various methods to transfer quantum states and to couple distant qubits. And one of the most straightforward methods is the direct swap operation between the nearest neighbor spins. And so my work here is going to demonstrate a way to improve the quality of the swap operation using a Fouquet sequence. And so I'd like to point out that the swap operation that I'm specifying here is the projection swap. In other words, we are only investigating the swap applied to spin eigenstates. And nevertheless, the high fidelity projection swaps can be useful for quantum computing applications, such as reading out a long spin array. And now here is a typical semiconductor quantum dot device we use in our experiments. It is a quadruple quantum dot array. Let me pull up my laser pointer. So here is the quadruple quantum dot array, and it's fabricated on a gallium arsenide, aluminum gallium arsenide heterostructure. And the electrons will reside in the interface between the 2 materials, and the confinement potential are formed and controlled by the voltage applied to the metal gates on the surface of the wafer. There are also 2 extra quantum dots on the top of the main array, and they serve as charge sensors for readouts of the left pair and the right pair of the electron spins. We normally operate in the regime where only one electron occupies each quantum dot, and we can control the number of the electrons by adjusting the chemical potentials or the depth of each quantum dot. And we can also control the coupling between the neighboring spins by adjusting the height of the potential barrier. And all of these are controlled by applying different voltages on the metal gates on the top. And the system dynamic is governed by this Heisenberg exchange model shown in this box here. And we label the exchange coupling as J. And so moving on to the actual experiment. So in our quadruple spin array, we can prepare the left two spins into an anti-aligned product state. So either an up-down or a down-up state. And similarly, we can also prepare the right two pairs, the right two spins in the right pair as also another anti-aligned product state. And then we can apply the swap operations to both pairs simultaneously by turning on the exchange coupling between each pair. Now, normally the swap operation, the swap pulse is highly susceptible to pulse timing errors and noise in the environment. And so, for example, in our device, the major source of noise is the hyperfine noise coming from the nuclei in the semiconductor substrate, or the charge noise coming from some kind of two-level system defect in the nearby materials, or coming from the metal gates on the top. We can, however, make our system more robust by adding an interaction period right after the swap pulses, which requires turning on the coupling between the middle two spins. And now we refer to this combination of swap and interaction as one full case step. And we can repeat the step multiple times and measure at the end and see what is the initial state return probability of the system of each pair. And now to better visualize exactly what is the effect of this repeated full case sequence, we first initialize each spin pair into the anti-aligned product state, like I mentioned earlier, and then measure them after 4 full case steps. And during this 4 full case steps, we can sweep the interaction strength as well as the intentionally added swap pulse errors. And then we can obtain this effective phase diagram. And so in this phase diagram, it's plotting the initial state return probability of each pair. And as you can see, there are periodic diamond-shaped patterns, which represent the high return probability, the yellow shape, the yellow color, the high return probabilities after 4 full case steps of each pair, which indicates the enhancement of the swap operations. And so we identify the center of the first diamond as the optimal interaction strength for best swap improvement. And furthermore, at the optimal interaction strength, we can see that the enhancement region is further extended along the y-axis, which is the added pulse error. And that indicates that the system is now more robust against pulse errors. And we further quantify the effect of this enhancement by comparing the quality factor of this full K enhanced spin swaps with the regular spin swaps. And once we have identified the optimal interaction strength here, we apply the full K sequence up to 50 steps and measure the return probability of both pairs at each step. And for regular spin swap, we simply turn off the interaction entirely. So this interaction here, so we just turn it off. And then again, measure the return probability at each step. And as you can see here, by comparing these two types of swap operations, blue being the enhanced spin swap and red being the regular spin swap, we found an approximately 3-fold enhancement of the quality factor on spins 1, 2, or the left pair, and then an approximately 9-fold enhancement of the spins 3 and 4 swap. And so to understand this enhancement from a different perspective, we can actually make a connection between our experimental results with a novel state of matter, which is the discrete time crystal. And so a discrete time crystal is a phase of matter that has been recently discovered or recently experimented with. And it's something that breaks the discrete time crystal translational symmetry, discrete time translational symmetry. And a prototypical example of such system is a periodically driven Ising coupled spin chain. And one of its crucial properties is the robustness against interactions, driving pulse errors, and noise. And so recent experimental works have observed this discrete time crystalline behavior in several platforms, such as the trapped ions, MV centers, NMR spins, and transmon qubits. Although I believe some results are sort of under debate whether they are truly demonstrating time crystal phase or not. But regardless, one platform that has never seen discrete time crystal is the semiconductor quantum dots. And so I'm going to highlight a few points about the connection between our device and the proposed system of the true time crystal phase. And so if you look back to our quadruple spin array here, instead of treating it as a 4-spin system, we can group the left 2 spins together and treat them as one singlet triplet qubit, as long as they're prepared in the 0-spin magnetic moment. Similarly, we can treat the right 2 spins as another singlet triplet qubit. And so in this case, what we consider to be the spin swap operations are essentially a pi rotation of the singlet triplet qubit. And so what we have effectively here is an Ising coupled 2-qubit system that are undergoing periodic pi pulses and exhibit subharmonic responses, as well as an improved quality factor and robustness against pulse errors and noise given the right condition. Now, we are not claiming that our system is in time crystal phase, since a true time crystal requires a much larger system size. And as a matter of fact, one might notice that what we have shown here is essentially a form of dynamical decoupling. And instead, what we are trying to demonstrate is a precursor to realizing a time crystal in semiconductor quantum dot arrays, as well as the potential applications of discrete time crystals in quantum computing, such as the enhancement of the projection swap operations. And so here are a few potential applications for this 4K sequence protocol in a quantum dot spin array. And first is the high fidelity projection swaps, like I mentioned earlier, and this can enable a reliable readout of the inner spins in a long spin array, especially for the standard Alderman readout or spin selective readout. We have also theoretically explored the possibility of preserving 2-spin entangled states using this 4K sequence. And our simulation shows that the singlet state or the T0 state can be preserved with a much higher fidelity and longer coherence times compared to the regular spin echo pulses. And finally, given the singlet triplet qubit Ising interaction, we can easily incorporate this protocol into a 2-qubit gates into this 4K sequence protocol. And so to summarize, we have demonstrated the enhancement of the spin eigenstate swaps in our device using a 4K sequence. The behavior and the condition of such enhancement resembles the discrete time crystalline phase, and our work indicates the possibilities of realizing a true discrete time crystals in semiconductor quantum dot spin arrays, and the possibility of applying such time crystal physics to the spin-based quantum information applications. And with that, I'd like to thank you for your attention, and I'll take any questions.
Thank you so much for your presentation. I would like to mention that your question was, what are some of the important skills that the employers are looking for when hiring for the experimental quantum computing research scientist position? Particularly, what makes the employer want to hire someone who comes from a different research background than the company's research direction, for example, spin versus transmon and so on. So now if anybody has any answers or any questions, please go right ahead.
So I'll jump in. I'm not that I'm an expert in this area, but I would say certainly you'd want to focus on trying to get a job at a company that's doing, using the qubit modality that you're used to working in, doing your research in, right? But that said, you're obviously all really smart. So in theory, if there was a company where maybe the culture felt more aligned with your values or morals or ethics or worldview, but maybe the technology wasn't exactly what you've been working on, I would say if you hit it off and you felt comfortable and the potential exists for you to work at a company where they would maybe train you or orient you or redirect you or upskill you, as they say in HR parlance, right? So I would encourage you to explore. I mean, I wouldn't be limited by the tremendous research you've been doing. And I don't mean to demean it at all. It's fantastic what all you've been doing. But the idea is operating at the level that you're all operating at. You know, maybe there's a company you've been doing spin, but you are interested in, you know, trapped ions or transmons or nitrogen vacancy, whatever. You know, explore, be open to trying a new modality, if you will, because this business is growing really fast, and they're looking for really smart people like all of you. And I'm pointing to the presenters, you know, to get engaged. So onward.
That makes sense. Thank you.
Yeah.
So because of our fluctuating style, it just happens this way. A number of people had to jump off, but before they left email. For example, Jeff Joy from Cold Quanta was asking who they can follow up with. I'm going to send them your emails. I also want to remind that June 30 is when we have our next session of office hours. We'll still take questions if anybody has questions.
I would also say, please connect with me on LinkedIn. I know Harper and I just connected, but again, LinkedIn, at the risk of sounding pedantic, is the lingua franca, right? It's the coin of the realm. It's where recruiters, hiring managers, executives, peers, HR people are going to go to look to see who you are and what you do and what you know how to do, what kind of deliverables and work products you've created in your academic setting. So I encourage you to trick out your LinkedIn profile and connect with me, with Adrian, with anyone else on the call. When Adrian distributes this list, you know, go on LinkedIn and connect with everybody, right? This is a very unique community, QED-C, and we're all passionate about moving the needle and, you know, doing whatever we can to drive understanding and adoption of the quantum information science and the potential benefits it can deliver to society and business and culture. So I'm waxing philosophic at the end there, but that's the deal. Just saying. Right?
We're going to share your information with Charles. Charles is not here. He's leading the public sector at IBM Quantum and all the industry members. And if you come join the office hours, then they're going to reach out to you and so on. Okay, so with this, if nobody has any other questions, Harper, Andy, Sean, and Haifeng, thank you so much for being part of our session today.
Thank you so much for having me.
Thanks for having us.
Job.
Thank you. Thank you for having me.
We're gonna post the recording in a few days, and we'll let you know, and we'll follow up with you. Thank you so much. We'll see you next time.
Thank you. See ya.
Thank you.
Bye.
Nice job, Adrian.
It was difficult, wasn't it? With the sound, something happened. I don't know, but
We always go long. We should
Thank you,
book these for like an hour 15, because that seems to be what we.
yeah, we normally stop
Hey.
after 90 minutes. Yeah. Okay.
No,
Thank you.
Sean, that was great doing a recording.
Oh,
You have a-
yeah.
You
Thank
have a
you.
new
One that-
baby? Is that what happened? Is that
Yeah,
going
I
on?
had a baby, and you know, they're asleep behind me. I didn't want a suddenly screaming baby to interrupt my my
Yeah.
presentation.
Well,
So,
congratulations on that, man.
thank you so
Enjoy.
much. And thank you again for the opportunity to present this even in a recorded fashion. It was really great.
Yeah, no, it's great. All right. Continue the great work.
Appreciate it. Thank you.
All right.
Bye-bye.
See ya.